Good afternoon, folks. My name is Patrick McConnell. From Vancouver, British Columbia. I'm the president and CEO of Atlantis Fiber. Atlantis has developed carbon neutral applications within the concrete and built environment. And it's my pleasure to speak to you today about one such application that we feel is greatly needed around the globe. To further emphasize this point, allow me to play this short video showing the recent devastating earthquakes in both Turkey and Syria. So this is aerial footage of before and after in Turkey specifically. You can see the unbelievable, devastation. Primarily, a lot of these buildings were of unreinforced masonry, and that's kind of the initial discussion point of our presentation today. We've subsequently learned, unfortunately, that sort of flaws in building code didn't help matters much. So that's another issue, but primarily, we just wanted to underscore that unreinforced masonry certainly suffered the brunt of a lot of this devastating damage that you see before you. All right, so with that rather kind of sobering look at the ultimate negative impacts of unreinforced masonry and highly seismic zones, this slide sort of just denotes the overall global necessity for seismic retrofit. 40 billion meter cubes or cubic yards of retrofit composite is a pretty staggering number, obviously. But I think when you look at the overall slide here, starting in Europe all the way through the Middle East, obviously with Turkey and Syria being the most recent sort of victims of earthquake action, all the way through Southeast Asia, down to even New Zealand, up through Japan, of course, and then finishing off in North and South America on the West Coast. Even areas, of course, in the Caribbean are highly prone to earthquakes, such as we've seen in Haiti, and areas that aren't even on this slide, such as Salt Lake City and Utah, is a highly seismic area with actually a large proportion of unreinforced masonry in that particular state as well. So what are some of the solutions? I think Atlantis has innovated a few different technologies over the last couple of years, one being seismic fiber, or the more technical term would be engineered hybridized cementitious composite. Some of the benefits of this particular application are its carbon neutrality. We use a high percentage of industrial byproducts, which I'll touch on the ensuing slides. And of course, we use very little cement, which, as we know, is a large contributor to carbon detrimental effects throughout the globe. So the further you can drive down the cement content, the better. And quite a diverse series of applications. You can see this robotic arm being one. We can use a hopper spray and even hand trowel application as well, opening up a lot of sort of options for the applicators. So as I touched on the the upcycled and industrial byproducts, one of the main components of what we're using in our EHCC application is that of recycled and upcycled polymer-based fiber from that of recycled tires. We've been working with one of the largest tire recyclers within North America and a company called Liberty Tire over the last number of years. And we've kind of delved into some R&D with them. And this is one of the main proponents, which I'll touch on, that really underscores the circular economy and the sort of carbon neutral aspects of what we're claiming for these particular applications. So this video is just a quick short demonstration that we've obtained from the University of British Columbia in their seismic earthquake lab facility. It basically mimics the 9.1 magnitude event that took place in Fukushima, Japan back in 2011, which is, as we know, caused an amazing amount of devastation with the ensuing tsunami as well. So this is a demonstration of a wall with the HCC applied. You can see the high ductility. And here's a side-by-side comparison in forced versus non-reinforced. It actually collapsed at about 65% of the 9.1 earthquake, whereas this, we had ratcheted up to about 200% of that seismic level in order to get it to even fail. So it shows a pretty remarkable increase in ductility. So moving on from that demonstration, just want to draw your attention to the load displacement curves. If you can look to the far left, which is denoted by mix 0 on the legend, you see kind of an inverted V, which basically shows that an unreinforced cementitious composite, which is what mix 0 is, demonstrates early strength, decent early strength, and when any significant load or displacement is applied, it abruptly fails to 0, which is to be expected with cementitious composites. But if you look at mixes 1 through 11, you see a pretty massive increase in ductility based on our EHCC applications. And further diving into that, what we find is quite interesting from an application perspective is if you look at the post-crack residual strength curves, again, the far left vertical line is denoted by mix 0 and just a purely cementitious composite. But if you look at mix 1 through 11, you can see a very kind of a variance in the overall performance and ductility of these particular mixes. And why that's important is because you don't necessarily need, bulletproof, let's say mix 8 type of ductility, other than places that are highly seismic with the real potential threat of high Richter magnitude events, such as Japan and parts of India and Southeast Asia, for example. So what that offers us is the ability to kind of play with the mixtures so that if you don't need the highest performance, you can look to a mix, for example, 3 or 1 in this instance, which would allow us to increase the level of industrial byproducts, further driving down the carbon impact. And this is a basic look at some of the global warming potential energy work we have done, comparing virgin PET fiber to recycled tire fiber sourced from BC, Alberta, and the entire kind of west coast of the US. You can see a pretty massive difference in the actual GWP potential, and kind of why we chose BC, Alberta, and in particular the US West Coast, because they're highly seismic areas. And we feel that we can have a pretty large impact among those particular regions. And it just goes to underscore the claims that we're making about effectively a carbon neutral product when you combine the other factors of the EHCC mix. This was a kind of a study commissioned by the Athena Sustainable Materials in combination with WAP Consulting. We took 3 buildings from their inventory, one on the university campus of UBC, campus of University of Massachusetts, and a building Lafarge had erected. And if you look at the total meter cubed on the second column to the left, you look at 12,000, 8,000, and just shy of 1,500. That was the total amount of square footage of concrete in these particular buildings. And right next to that is the associated GWP potential. Now, if you look, what's interesting here is the EHCC shotcrete. If we were to have just retrofitted these particular buildings as opposed to tearing them down at the end of their service life and rebuilding them again with fresh concrete, you only effectively would need 2165, let's say, and 14 meter cube of this very thin set application. So you can see a stark difference in the materials used for retrofit versus rebuild. In fact, in the last 2 columns to the right, it shows a comparison that it would take about less than 1% of the brand new materials to retrofit versus a complete demolition or rebuild of that exact same structure. So obviously shows a very powerful reduction in materials and therefore the improvement of the sustainability components of this application. And kind of what we're branching off from the initial slide where I talked about retrofit versus carbon capture. This is a powerful model that we think has a lot of potential legs to it. If you look at aging infrastructure in general, it can take 1 of 2 paths. Either the building or bridge, any basic concrete structure that could be reinforced can be reinforced in this particular case. It's typically torn down at the end of its service life, which constitutes new CO2 and new concrete formation, and of course the associated landfill waste due to trucking and other expenses. Whereas path B, if we were to apply the EHCC application, there would be no new 0.2 for between 30 to 50 years, and a net positive increase to landfill use, which I'll touch on here in the next couple of slides. So path B expanded. Basically, if you look at 3 categories of carbon capture and cost savings, waste mitigation, and then carbon offsets, we apply the EHCC, which is in itself a carbon neutral material. We store the original CO2 in either the building or other concrete structure for an additional 30 plus years. Another benefit there is a significant reduction in construction labor, which was problematic, and I'll touch on here in a moment as well. But what that does is it mitigates new concrete being formed, the great abatement of landfill waste, which is detrimental from an environmental and cost perspective. We feel this will encourage the building structure reclamation in the future, kind of the desire for this model to continue. And then lastly, this is kind of a potentially interesting and substantial bonus is that we feel we can exchange the CO2 credits and carbon offsets back to the cement industry, which, as we all know, are very interested in driving down their imprint, or the carbon markets in general, for an additional kind of revenue stream and benefit to the overall user. So as I touched on before, landfill waste, this is just an average of $150 a ton based on kind of Europe and North American numbers, but you can see quite easily that this adds up very quickly when you're dumping large amounts of heavy concrete and aggregate into the landfill space. Not to mention, as I just touched on, the environmental detrimental aspects of increasing landfill in general. And then, of course, carbon credits and offsets, which I touched on in the last circular model. There's no secret that these are only going to be larger constraints through governments and initiatives in the next years to come. It varies from Europe to North America to other parts of the world in terms of the actual cost, but I think that we can all agree that this is something that large companies like or industries like cement and concrete are very keenly aware of, and we think we can help sort of drive down these potential business issues with this particular model. As I touched on, labor shortage is a real concern. Pretty staggering stats here of 600,000 skilled construction workers, shortage thereof, that is. And with every $1 billion in infrastructure spending requires an additional 1,300 workers. So as I touched on in the earlier slide, we can largely automate this process, which further reduces the amount of workers actually required. And also when it comes to retrofit versus demolition and complete rebuild, there's a very stark difference in the actual labor required for that application as well. And then lastly, just want to touch on the broader applications. We talked about primarily building, retrofit, commercial and residential. But as I mentioned, there's also transportation from roads to bridges to SkyTrain, LRT, light rapid transit, reclamation and restoration. And underground infrastructure, we started some work on looking at box water culverts, which are concrete, even sewerage applications. I mean, there's an amazing amount of concrete beneath our feet in every developed city, and we feel that we can actually play a role in really improving the ductility and quality of these structures, thereby prolonging their life expectancy as well. And with that, thank you for your attention, folks. You can, for more information, look at atlantisfiber.com or atlantisfiberbrochure.com to find a little bit more. And of course, feel free to reach out to me directly. I'd be happy to answer any questions that you may have. Thanks very much for your attention.